This is an example to show you how to classify critical points of function of two variables into maximal, minimal, and saddle point. In this example, we are going to locate all relative extremer and saddle points of the function f of xy equal to 4xy minus x power 4 minus y power 4. Partial differentiation of f with respect to x is equal to 4y minus 4 times x power 3. And set it equal to 0, we have equation 1. Partial differentiation of f with respect to y is equal to 4x minus 4 times y power 3. Set it equal to 0, we have equation 2. From equation 1, I have 4y minus 4x cubed equals 0 or 4y equal to 4x cubed. So y equal to x cubed. From equation 2, I have 4x minus 4y cubed equal to 0. So x eventually equal to y cubed. Substitute y equal to x cubed into here. I get x equal to x power 3 raised power 3. So x equal to x power 9. So how do we solve equation like this? So x is equal to x power 9 means x power 9 minus x equal to 0. Factor out x, we get x power 8 minus 1 equal to 0. From here, we can deduce that x equal to 0, 1 minus 1. Using equation 1, we have y equal to x cubed. Therefore, when x equal to 0, y equal to x cubed is equal to 0. So, first critical point is x equal to 0, y equals 0. When x equal to 1, y equal to x cubed is also equal to 1. So another critical point is x equal to 1, y equal to 1. And when x equal to minus 1, y equal to x power 3 is also minus 1. The last critical point is at x equal to minus 1, y equal to minus 1. After we have compute all the first order partial derivatives and the critical points, now we are going to classify these critical points using the second partial derivative test. We need to find out the second order partial derivative of f with respect to x, which is partial differentiation of f with respect to x 2 times. This is equal to partial differentiation with respect to x 4y minus 4x cubed, which is equal to negative 12x squared. And partial differentiation of f with respect to y 2 times is equal to differentiate f with respect to y 2 times. is partial differentiation with respect to y of 4x minus 4y cubed is equal to negative 12y squared. And partial differentiation of f with respect to x, then with respect to y. So it's partial differentiation with respect to y on 4y minus 4x cubed, which is equal to 4. And now we can compute d, which is partial differentiation of f with respect to x 2 times partial differentiation of f with respect to y 2 times minus partial differentiation of f with respect to x and then with respect to y squared. This gives us minus 12 x squared times minus 12 y squared minus 4 squared, or 144 x squared y squared minus 16. We can organize the computation in a table format. The left hand side, we have the critical points, which are 0, 0, 1, 1, and negative 1, negative 1. And then we need to compute the corresponding second order partial derivative with respect to x and also d based on the critical point. And then we can classify the nature of this critical point. So let's try to figure out the nature of critical point at 0, 0 using the formula of partial differentiation of f with respect to x 2 times. At the point x0, y equals 0, this value is 0 here, and value of d is 144 x squared y squared minus 16. When x0 and y0, d is equal to negative 16. To recap again, the second partial test states that if d is negative, then the function has a saddle point at the critical point x0, y0. Using the second partial test, we find that because d is negative, therefore 0, 0 is a saddle point. Next, we are going to classify the nature of the critical point at 1, 1. Using the formula for second order partial derivative of f with respect to x, this is equal to minus 12 times 1 squared, which is equal to negative 12. And d is equal to 144 times x squared times y squared minus 16, where x is equal to 1, y is equal to 1. This gives us 144 minus 16, which is equal to 128. And this is positive. Therefore, what is the nature of this critical point? Let's look at the second order partial derivative test again. Based on the second partial test, if d is positive and the second order partial derivative with respect to x is negative, then f has a relative maximal or local maximal at the point x0, y0. Coming back to the problem again, we find that the point 1, 1 is a local maximal or relative maximal. Finally, we look at the critical point -1, -1, where partial differentiation of f with respect to x 2 times is again equal to -12, where x squared is equal to 1 and d is equal to 144 x squared y squared minus 16, which is again equal to 144 minus 16 equal to 128, is again positive. Therefore, the nature of the critical point at -1, -1 is the same as the nature of critical point 1, 1. This is a local maximal. Therefore, this function has one center point and two local maximal points. Here is the graph of the surface. You see a local maxima here, a local maxima here, and a center point. Here is another view of the surface. You see a local maxima here, and a local maxima here, and a center point here. Here is a rotation view of a surface. You can see the surface at different view. Let's try to see the top view, side view, and within the surface. Notice that two local maxima point and one center point.